Hello dear students. So welcome back to my video lecture 7 on hydrogen and its compounds. So I hope you have watched my previous video wherein in my last video I have discussed about water, that is the oxide of hydrogen, that is water, the properties, physical properties of water, and then the structure of water in the vapor phase and in the solid state. That is, we have discussed the structure of steam and we have discussed the structure of ice, isn't it? So please just recall, hope you have seen it. Just recall once again. We have learned that water has high dielectric constant, water has high dipole moment. So I have told you in solid state and in liquid state, that is in condensed state, water will show some unusual properties, correct? Since water has high dielectric constant, it is a polar solvent. Since water has high dielectric constant, it is able to dissolve many solutes in it. That is why it is regarded as universal solvent. Since water has high dipole moment, it is a polar solvent. So like dissolves like. So polar solutes are soluble in polar solvents. Yes. So now in this video we will be talking about the chemical properties of water, and most importantly we will talk about hard water and soft water. Yes students, yesterday I told you that ice, the density of ice is less than that of water, and I have given you the reason for it also. Since in solid state, all the water molecules get condensed due to the formation of hydrogen bond. Do remember, one water molecule in the solid state will form 4 hydrogen bonds. So because of extensive hydrogen bonds, it leads to empty spaces. Inside water, between the water molecules there will be empty spaces, and those empty spaces, which are called as voids, will be filled with air, isn't it? So because of the accumulation of air in the voids, now density of ice becomes less than that of water. Now let us compare the volume of ice and the volume of water. Yes, let us compare the volume of ice and volume of water. Volume of ice and volume of water, for the same mass, same mass. Look here, yes, we know density is equal to mass by volume, isn't it? Yes, let us take volume is equal to what? Mass by density. Now I am comparing the volume of ice, is equal to what? Mass of ice divided by density of ice, and volume of water is equal to mass of water divided by density of water. Is that correct? We know density of ice is less than the density of water. Since density is less, volume will be more. Since density is more, volume will be less. Are you able to understand? Since the density of ice is less than the density of water, since density is less, volume of ice will be more, but density of water is more, hence the volume of water will be less. For the same mass is same. For the same mass, density of ice is less, hence it has more volume. For the same mass, density of water is more, therefore it has less volume. So please remember this point. Always for the same mass, volume of ice will be more than the volume of water. Yes, remember this. Volume of ice will be more than volume of water, correct? Next we will talk about the density of water. Now if I talk about density of water, please note this point. Now water has maximum density at 4 degrees centigrade. Okay, yes, water has maximum density at what temperature? 4 degrees centigrade, and it decreases above and below 4 degrees centigrade. Okay, below what? 4 degrees centigrade. Please note this point. Okay, water has maximum density at 4 degrees centigrade, and it decreases above 4 degrees centigrade and below 4 degrees centigrade. Okay, so water density is maximum at what temperature? 4 degrees centigrade. Below 4 degrees centigrade, okay, density decreases. Above 4 degrees centigrade, above 4 degrees centigrade also density decreases. Okay, we know at 0 degrees centigrade, which is less than 4 degrees centigrade, at 0 degrees centigrade water exists in the form of what? Ice, correct? Okay, at 0 degrees centigrade water exists in the form of ice. We know density of ice is very less than that of what? Water, pure water. Is that correct? Okay, yes. So density of water will be less below 4 degrees centigrade, and it will be less above 4 degrees centigrade. Okay, so at 0 degrees centigrade, since it exists in the form of ice, density of ice is less than that of water. Now let us keep on increasing the temperature. Okay, if I keep on increasing the temperature from 0 degrees centigrade, what is going to happen? The hydrogen bond in ice breaks. Okay, the hydrogen bond in ice starts to break. When the hydrogen bonds starts to break, what will happen? Okay, ice starts getting converted to what? Liquid water, isn't it? Ice starts getting converted into liquid water. Okay, yes. So when I increase the temperature from 0 degrees centigrade, the hydrogen bond in ice starts to break. Okay, when the hydrogen bond in ice starts to break, ice, okay, gradually starts getting converted into what? Liquid water. We know volume of liquid water, before just few minutes back we understood that volume of liquid water is less than the volume of ice. Okay, we know density is equal to what? Mass by volume, isn't it? Volume of water is less than the volume of ice. Since volume is less, density will be more. Okay, density will be more. Okay, so when the temperature keeps on increasing up to 4 degrees centigrade, at 4 degrees centigrade, ice completely melts to form what? Liquid water. Okay, and liquid water starts, the molecules of liquid water will starts to develop hydrogen bonding starts to develop in what? Liquid water. Okay, and now again what will happen? Okay, when the hydrogen bond starts to develop, what is going to happen? Volume is going to decrease. Okay, yes, volume is going to decrease. Okay, so after 4 degrees centigrade, okay, what might happen? After 4 degrees centigrade, okay, there will be pure water, there will be no ice. After 4 degrees centigrade, there will be pure water, there will be no ice. We know that. Okay, yes, pure water. Okay, as the hydrogen, because of extensive hydrogen bonding, what will happen? Density, okay, density is more. Density, what is going to happen? Density is equal to mass by volume. Okay, so after 4 degrees centigrade, ice completely melts to form water. Okay, volume of water decreases. Okay, sorry, volume increases. As volume increases, density is going to decrease. So above 4 degrees centigrade, density decreases. Okay, below 4 degrees centigrade, density is less. At 4 degrees centigrade, density is maximum. Okay, so density will be maximum at what temperature? 4 degrees centigrade. That is what I mean to say. Okay, so water has maximum density at 4 degrees centigrade and decreases above and below 4 degrees centigrade. Okay, yes, that's correct. Okay, apart from that, okay, we have discussed the polarity of water. Water is a polar solvent, isn't it? Okay, we have discussed the polarity of water. Water is a polar solvent. Why water is a polar solvent? Because of the electronegativity difference between oxygen and hydrogen. Okay, there is electronegativity difference and there is a net dipole moment. Okay, and the dipole moment, okay, please watch my previous video. The dipole moment of water is found to be equal to what? 1.84 dBi. Okay, very high dipole moment, hence it is a polar solvent. Okay, so since it's a polar solvent, it dissolves polar solutes. Okay, it dissolves what type of solutes? Polar solutes. Okay, yes. Now with this background, okay, let us talk about the chemical properties of water. Let us talk about the chemical properties of water. So under chemical properties, okay, we'll be talking about the amphoteric nature of water. Amphoteric, okay, nature of water. Okay, we will be talking about, okay, yes, reducing nature of water. Reducing nature of water. And then we'll speak about what? Okay, hydrolysis. Hydrolysis. And lastly, we will talk about the different hydrated salts. Hydrated salts. Understood? Okay? Yes. Yeah. Okay. So we will talk about these different chemical properties of water. Okay. Yes. Amphoteric nature of water, reducing nature of water, hydrolysis, and hydrated salts. Okay. What do you mean by amphoteric nature? Okay. Yes. Amphoteric nature. What do you mean by amphoteric nature? See, if the same substance, okay, if the same substance behaves, okay, both as an acid as well as a base, if the same substance behaves both as an acid as well as a base, then that substance is called as amphoteric. Yes, water is amphoteric in nature. Let us prove that water behaves both as an acid as well as a base. Okay, water behaves both as an acid as well as a base. I'll take some examples to show, okay, that water behaves both as an acid as well as a base. Let us treat ammonia. Okay, ammonia with water. What happens when ammonia is treated with water? When ammonia is treated with water, yes, it will form NH4 plus, okay, and OH minus. Look at here. Okay, it will form what? NH4 plus and OH minus. Okay, how did NH4 plus and OH minus ion is formed? Okay, so ammonia, when it is treated with water, it is giving NH4 plus and OH minus ion. How did NH4 plus and OH minus occur in this reaction? How did NH4 plus and OH minus form in this reaction? Okay, look here. When nitrogen accepts H plus ion, okay, from water, it will form NH4 plus. Okay, when water gives one hydrogen to, okay, NH3, it will become what? OH minus, isn't it? OH minus. That means here NH3 is acting as H plus ion acceptor and water is acting as H plus ion donor. H plus ion donor. According to Bronsted theory of acids and bases, we have learned that any species which accepts H plus ion is said to be a base. Okay, any species which donates H plus ion is said to be a acid. So in this case, water is behaving as an acid. Okay, water is behaving as an acid, correct? Okay, yes, this is base and this is acid. Okay, so what is this then? This is going to be what? Conjugate acid. This is going to be what? Conjugate acid, and this is going to be what? Conjugate base. Conjugate base, isn't it? Okay, this will be conjugate acid and conjugate base. Any doubt? Okay, yes, the base conjugate acid. Okay, acid conjugate base. Any doubts with this? So in this example, water is behaving as an acid. Let me consider one more example wherein hydrogen sulfide reacts with water. Okay, when hydrogen sulfide reacts with water, it is going to form, okay, yes, HS minus and H3O plus. Okay, when hydrogen sulfide reacts with water, it is going to form HS minus and H3O plus. How are HS minus and H3O plus ions are formed? How are they formed? Okay, so this is formed when, okay, hydrogen sulfide donates one H plus ion to water. Okay, so when H2S, hydrogen sulfide donates one H plus ion to water, it is going to become H3O plus and H2S will become HS minus. Okay, so that means in this case water is behaving as H plus ion acceptor. Okay, when water behaves as an H plus ion acceptor, okay, then it is going to be what? According to Bronsted theory, this is going to be base. Okay, and hydrogen sulfide is donating H plus ion to water. This is going to be an acid. This is going to be acid. Correct. Observe this reaction here. Okay, so in this reaction water is acting as an acid. In this reaction water is acting as a base. So water behaves both as an acid as well as a base. Therefore we can say that water is amphoteric in nature. Water is amphoteric in nature. Okay, that's so wonderful. Okay, or I can also explain the amphoteric nature of water by a reaction called as autoprotolysis. Protolysis. I can also explain the amphoteric nature of water by using what? Autoprotolysis. Okay, what do you mean by autoprotolysis? Yes, when water reacts with water. Okay, this is the reaction between two water molecules. What is going to happen? One water molecule will donate H plus ion to another. Therefore, this is going to become OH minus. Okay, when the other water molecule will accept H plus ion, this is going to become what? H3O plus. Okay, so one water molecule is donating H plus ion to what? This water, and this water is becoming H3O plus and this water is becoming what? OH minus. So here one of the water molecule is acting as acid, the other water molecule is acting as a base. So this reaction will surely tell us that, okay, water is amphoteric in nature. Water is amphoteric in nature. So wonderful. Understood? Okay. Yes. Now let us talk about the reducing nature of water. Let me consider two different reactions. Okay. Let us consider two different reactions. What is it? Okay. What happens when sodium is dissolved in water? What happens when sodium is dissolved in water? Okay. Any idea? When sodium is dissolved in water, it will form sodium hydroxide, and hydrogen gas will be liberated. Hydrogen gas will be liberated. Is that correct? Okay. What is the oxidation state of sodium here? 0. It is in elemental state. Okay, uncombined state. Therefore its oxidation state is going to be 0. What is the oxidation state of sodium in sodium hydroxide? It is going to be +1. Okay, what is the oxidation state of hydrogen in water? +1. Oxygen -2. Here also oxygen is -2, hydrogen is +1. Now look at here, sodium is going from 0 to +1 state. Okay, yes, sodium is going from 0 to +1 state. 0 to +1 state. Okay, so that means sodium is getting oxidized. And look at here. Okay, yes, hydrogen is getting, okay, is going from +1 state to 0 state. That means hydrogen is undergoing reduction. Okay, so here, okay, sodium is getting oxidized. Okay, yeah, hydrogen of water is getting reduced. So don't you think this is the best example for a redox reaction? Okay, it is a best example for redox reaction, isn't it? Okay, so sodium goes from 0 to +1, it is oxidation. Okay, it is oxidation. So here water is oxidizing sodium to sodium hydroxide. Okay, water is oxidizing sodium to sodium hydroxide. Okay, there it itself is getting reduced to hydrogen. It itself is getting reduced to hydrogen reduction. Therefore this is the best example for redox reaction. This is the best example for what type of reaction? Redox reaction. I can give you one more example where 6 molecules of carbon dioxide, it is nothing but a photosynthesis reaction. Okay, yes, 6 molecules of carbon dioxide combines with 6 molecules of water to give what? Yeah, in the presence of sunlight. In the presence of sunlight, it will give C6H12O6 plus what else? C6H12O6. Okay, then 6 carbon. Okay, sorry, it is 12H2O. Okay, yeah, 12H2O, C6H12O6 plus 6 molecules of hydrogen, correct, plus 6 molecules of oxygen. Is it balanced now? Okay, 6 2s are 12, 12 plus 12 is 24, 6, okay, 6 oxygen, okay, 12, 12, 18, getting 18 oxygen, 6 carbon dioxide, 12 oxygen plus 12, 24, okay, 24, C6H12O6, 6 carbon, okay, yeah, we will get 6 molecules of water and 6 molecules of oxygen. Observe here, what is happening in this reaction? What is happening in this reaction? Yeah, okay, you can observe this is another example for redox reaction. This is another example for what type of reaction? Okay, redox reaction. Redox reaction, understood? So these two nature will depict, these two reactions will depict the oxidizing nature and the reducing nature of water. That means water, in some case it can act as an oxidizing agent, and in the other case it acts as a reducing agent. Okay, so water can behave both as an oxidizing agent as well as a reducing agent. Okay, yes, any doubts? Correct. Okay, so that's about the reducing nature and the oxidizing nature of water. Okay, now what about hydrolysis reaction? Okay, what do you mean by hydrolysis reaction? Yes, what do you mean by hydrolysis reaction? Hydrolysis reaction. Hydrolysis reaction. What is hydrolysis? Hydrolysis is nothing but hydro plus lysis. Lysis means break. Okay, breaking the molecule by adding water. Breaking the molecule by adding water is called as hydrolysis. Okay, now if I take P4O10, P4O10, okay, let us treat this with water. Okay, let us treat this with water. Okay, when P4O10 is treated with water, what is that you're going to get? H3PO4. Okay, H3PO4. Okay, correct? Yes, so we will get 6 water molecules here. Okay, P4O10, okay, is hydrolyzed to what? Phosphoric acid. P4O10 is hydrolyzed to phosphoric acid. Phosphoric acid, is that correct? Okay, and also if I take silicon tetrachloride, okay, treat it with water. Silicon tetrachloride is treated with water. Okay, what happens when silicon tetrachloride is treated with water? It gives silicon dioxide and 4 molecules of HCl. Okay, it gives silicon dioxide and 4 molecules of HCl. Okay, see here silicon tetrachloride is hydrolyzed to silicon dioxide. P4O10 is hydrolyzed to what? Phosphoric acid. Okay, so these two are the hydrolysis reaction. Like that, there are so many hydrolysis reactions. Okay, but in our NCERT textbook, under water we have these reactions to study. So please concentrate on these reactions. Okay, these reactions depicts what? Hydrolysis nature of water. What is hydrolysis? Hydro plus lysis. Lysis means to break the molecule by adding what? Water is called as hydrolysis. Okay, P4O10 is hydrolyzed to H3PO4, phosphoric acid. Silicon tetrachloride is reduced to silicon oxide. Silicon oxide. Any doubts? Okay, yes, that's correct. Okay, so next one, let us talk about, let us talk about the next reaction, what is called as hydrated salts. Hydrated salts. Okay, what do you mean by hydrated salts? Guys, we have come across 2 types of copper sulfates, isn't it? What are those 2 types of copper sulfate? One is just CuSO4 and the other one is CuSO4.5H2O. Okay, what is the difference between this copper sulfate and this copper sulfate? This is called as anhydrous copper sulfate. Anhydrous copper sulfate. Okay, anhydrous copper sulfate, whereas this is called as hydrated copper sulfate. Hydrated copper sulfate. Okay, yes, correct? So this is anhydrous copper sulfate and this is hydrated copper sulfate. Okay, yes. See, if water molecules are associated with a compound, if water molecules are associated with a compound, okay, then it is called as, then that compound is called as hydrated compound. Hydrated compound. For example, BaCl2, barium chloride dot 2H2O. What is this? This is hydrated barium chloride. If water molecules are associated with a particular compound, then that compound is called as hydrated compound, and these water molecules associated with the compound, they are called as water of crystallization. Water of crystallization. They are called as water of crystallization. Understood? Okay. So if water molecules are associated with a particular compound, okay, then that is known as water of crystallization, and the whole compound is called as what? Hydrated compound. Well, these hydrated salts are of three types. Okay. Well, the hydrated salts are of three types. What are three types of hydrated salts? One is called as coordinated water. Second one, it is called as hydrogen bonded water. Okay, water. And the other one is called as interstitial water. Interstitial water. Okay, yes, interstitial water. Okay, well, hydrated salt, okay, they are of three types: coordinated water, hydrogen bonded water, and interstitial water. For example, okay, coordinated water, for example, CrH2O 6 times 3 plus, okay, NiH2O 6 times, okay, 2 plus. So these two are the best examples for what type of hydrated salt? Coordinated water. Okay, why? Because here this is called as complex salt. This is called as complex salt. Anything which is written inside the square bracket, they are called as coordination compounds, and the salt is called as complex salt. Okay, in the complex salt, this is called as metal ion and this is ligand. Metal ion and ligand. Okay, yes, are you able to understand my point? What does this ligand do? This is metal. Okay, this is metal and this is ligand. Okay, this is metal and this is ligand. What does ligand do here? Ligand will donate a pair of electrons to the central metal atom. Ligand will donate a pair of electrons to the central metal atom. Okay, and it will form a bond called as coordinate bond. It is going to form a bond called as what type of bond? Coordinate bond. Coordinate bond. Are you able to understand? Ligands, this water molecules will donate a pair of electrons to the central metal atom, okay, and they're going to form a bond, and what is that bond called as? Coordinate bond. So if all the water molecules that are present in the compound, okay, are bound to the central metal atom through coordinate bonds, then they are called as coordinated water. It is called as what? Coordinated water. If all the water molecules are bound to the central metal atom through coordinate bond, then it is called as what? Coordinated water. For example, okay, observe the structure of CrH2O 6 times 3 plus. Okay, it is going to be something like this. Look here, chromium. Okay, it is octahedrally surrounded by 6 water molecules. Octahedrally surrounded by how many water molecules? 6 water molecules like this. H2O. Okay, H2O. Then H2O. Yes, H2O. Yes, H2O and H2O. Okay, so here, yes, so water molecule will donate a pair of electrons to the central metal atom and it forms a bond. What is this bond called as? Coordinate bond. Observe here, since all the 6 water molecules that are present in the molecule are bound to the central metal atom through coordinate bond. So this is what type of compound? What type of bond is it? What type of compound? It is called as coordinated water. Okay, next, hydrogen bonded water. Okay, so what do you mean by hydrogen bonded water? Okay, yes, What is hydrogen bonded water? If I consider this example, CuSO4.5H2O. Look here, okay. So I told you this is water of crystallization, okay. So out of these 5 water molecules, 4 water molecules will form 4 coordinate bonds with copper, and 1 water molecule will form hydrogen bond with sulfate. Okay, out of 5 water molecules, 4 water molecules will form coordinate bond with copper, and 1 water molecule will form hydrogen bond with sulfate. So the structure is something like this. Okay, look at the structure. So 4 water molecules, okay, yes, 4 water molecules will form coordinate bond with, okay, copper. It will form coordinate bond with copper, okay, yes, correct. And another water molecule will form hydrogen bond with water. Okay, it will form hydrogen bond with water, So such type of, okay, hydrated compounds, such type of hydrated salts are called as hydrogen bonded water. And lastly, interstitial water. Okay, what do you mean by interstitial water? Okay, see, if I take the example, okay, I'm going to take the example of barium chloride dihydrate. Okay, barium chloride dihydrate. See here, these 2 water molecules, the 2 water molecules will be trapped inside the interstitial sites of barium chloride crystal. Okay, the water molecules will be trapped inside the lattice points. It will be trapped inside the interstitial sites of what? Barium chloride. For example, see, if this is the lattice site of barium chloride, okay, if this is the lattice site of barium chloride, look here, the empty spaces between the particles are called as interstitial sites. These empty spaces are called as interstitial sites. See, these water molecules will be trapped inside these interstitial sites. Okay, the water molecules will be trapped inside these interstitial sites. Okay, such type of hydrated salts are called as interstitial water. Okay, so with this, guys, okay, in my next video I'll be talking about hardness of water. Thank you.